So now that we kind of talked about how to write electron configurations, what is one thing that these electron configurations tell me? They tell me where all the electrons are located, but it also tells me some properties about the element. So it's going to tell me how that element is going to behave in regards to a magnet. And so the element's either going to be paramagnetic or diamagnetic. So paramagnetic are those with one or more unpaired electrons. So there's got to be at least one electron who doesn't have a partner for him to be para. A lot of times we think para, oh, they're all paired. That's not the case, okay? Para doesn't mean they're all paired. Actually, dia is what that means because dia stands for two, meaning there's two together. So don't get that mixed up. All right, diamagnetic are those with all paired electrons. So everybody's got a partner, a buddy. All of them are paired. There's at least one electron that's unpaired. So let's talk about the difference between these two. If I took one of the elements and I put it next to a magnetic field, how would it react? Those that are diamagnetic will be repelled by a magnetic field. So they're going to behave much differently than a paramagnetic, which is not affected by a magnetic field, where these guys are going to be repelled by a magnetic field. Okay? So what we want to know is we want to know where they're at based on the periodic table. So I'm going to pull up a periodic table and we can look at the periodic table and just be able to predict which one's which. Alright, so we want to be able to say who is paramagnetic and who is diamagnetic. Alright, so we want to talk about each column because remember we said that the columns have similar properties. So let's talk about column 1A. So let's look at lithium. So lithium, let's write its electron configuration. We start at the top here. So lithium would be 1s2 and then 2s1. Now, one thing that's helpful with these is to draw what we call orbital diagrams. So orbital diagrams are just kind of line pictures to show what's actually happening in each orbital. So my first orbital I have is an s orbital, a 1s orbital. So remember for an s orbital, there's only one picture, only one orientation, has only one ml value, and so that's 0. And so I only have one picture for it. So this is the 1s, one line, and it has two electrons. So one spin up, one spin down. That's where we get the positive 1/2 and the negative 1/2 for the ms. The next one is a 2s orbital. It's an s orbital, so it has one line, and it only has one electron in it. So that's what it looks like. So here, these electrons are paired up in the s orbital, but this electron is by itself. So based off our definition, if there's unpaired electrons, it's para. If they're all paired, it's dia. So since we have one electron unpaired, then that means that everybody in the lithium column is going to be paramagnetic. So we can say everybody in 1A is paramagnetic. Now let's do beryllium. Let's do the 2A. So beryllium is going to be the same thing, 1s2, but now it's 2s1, 2. So 2s2. So beryllium is 1s2, 2s2. So we've got the 1s orbital, and then the 2s orbital has 2 electrons in it. So in each of my s orbitals, this guy is paired and this guy is paired. So if all the electrons have a partner, if everybody's paired, then it's diamagnetic. So everybody in this column is diamagnetic. So everybody in 2A is diamagnetic. All right, let's come over here and let's do boron. So we add one more electron. So boron's 1s2, 2s2, and then we go over there and we're in the P. We're 2p1. So now we have to draw the pictures for the P. So remember the P has 3 different orientations in space. It's 3 mLs, -1, 0, and +1. So since there's 3 orientations in space, we draw 3 lines for the 2p, and there's only 1 electron, so we put the 1 electron in. So that 1 electron in the 2p is all by himself. So since he's all by himself, he's not paired with anybody, he's going to be paramagnetic. So this entire column, my 3A, is all going to be paramagnetic. All right, let's do the next one. The next one is carbon. So carbon's 1s2, 2s2, and then 2p1, 2. 2p2. Now, here's my choice. I can either put him here or here. And this is where Hund's rule. So Hund's rule says that we want to maximize the spins. We want to have the same spins before then we flip. So if I want the same spin, if I put him here, he's got to go the other way. So what that means, Hund's rule says I'm going to fill him up. Same spin first, and then I'll go and fill him in and give him a partner. So that means like I go up, 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 then down, down, down. So if I have 2 p's, I gotta put one here, and then I put the next one in the second p orbital. Okay? So that's why these pictures help, because if you looked at this, you would think there's 2 p electrons. They must be paired together. Everybody's paired, it must be dia. But that's not the case. These guys are paired, but I have 2 electrons that aren't paired. So because it's not paired up, it's going to be paramagnetic. So that column, which is column 4A, is paramagnetic. So now I'm going to do the next one. The next one is nitrogen. 1s2, 2s2, 2p1, 2, 3. Okay? So same thing. I want to fill it up. So I put 1, 1, and then I do the last one. All of the p electrons are by themselves, so they're all unpaired. So that means that nitrogen and everybody in his column is going to be paramagnetic. All right, let's do oxygen. So oxygen is going to be 2p, 1, 2, 3, 4. Okay? Same thing. We think there's 4. Oh, that must be 2 pairs. It's not true. We have to go 1, up, 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 and then the next one, now that each one of the orbitals has 1 electron, now we put in the 4th electron, which goes into this orbital by himself. Okay? So this first orbital is filled, and 2 of them, they're paired together, but the other 2 orbitals are not paired together. So these other 2 orbitals here, there's at least 1 electron by himself, so that makes all of these paramagnetic, the whole column. Now let's do fluorine. Fluorine's going to be 1s2, 2s2, 2p5. So same thing. We put in each electron by itself, and then we come back in and we fill it up. So now we have 2 pairs, but there's still 1 electron by himself. So as long as there's an electron by himself, he's going to be paramagnetic. So that whole column is paramagnetic. All right, let's do the last one. Let's do neon. Neon's 1s2, 2s2, 2p1, 2, 3, 4, 5, 6. So we go up, 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 down, down, and down. So now we can see that every single one of my orbitals has my 2 electrons, because remember the most you can have in an orbital is 2. And then everybody is paired up. So if they're all paired, then that means he's going to be diamagnetic. All right, so now if I know which column it is in, I can predict if it's going to be paramagnetic or diamagnetic. All right, so on the next slide, we're going to put it all together. We're going to write the electron configuration, write the orbital diagram, and I'm going to go ahead and ask you if it's paramagnetic or diamagnetic. So let's do the next problem, do the practice problem in the next lecture.